Alright, welcome. In this video, we're going to be practicing U-substitution. We're going to do a bunch of examples of indefinite integrals and definite integrals, and we're going to hopefully get that U to U pattern down. Okay, so first we've got 15 just like standard algebraic integrals, and I've got a couple other problems for you that are kind of interesting. Alright, now the first one is the antiderivative of sine of 4x with respect to x. And this is one that I want you to be able to just kind of jump straight to, okay, that's going to be negative cosine of 4x divided by 4. Okay, maybe plus a constant, okay, in the long run. But for now, if you need to, go through the U-substitution process to convince yourself of like how this works, this is a great time to do it. So we would say, okay, U equals 4x, so du dx would be 4, and du is 4 dx. But I don't have 4 dx, I have 1 dx, so I would just, solve for dx and say that's 1/4 of du. Okay, and then I would make my substitution. I'm still taking an antiderivative. There's still a sign. Nothing's changed about that. It's just 4x is now u, and the dx is at 1/4 and a du. Okay, and this is a much easier integral. The antiderivative of 1/4 of sine of u is going to be negative 1/4 of cosine of u plus c. And then we can see that, okay, with u equals 4x, that's actually the same thing. And the next two are very similar. E to the negative t over 3. We know e to the thing is very close to its own antiderivative if the thing is linear. Okay, if it's like something else, then we might be in trouble. We might need more solid U-substitution, or it just might not be possible. Okay, but e to the negative t over 3, this is going to be e to the negative t over 3, or maybe divided by negative 1/3. Okay, so that would be negative 3 e to the negative t over 3 plus c. And we could mentally take the derivative with the chain rule, say negative 3 e to the negative t over 3 times negative 1/3. That would give me that positive 1 I'm looking for. Okay, but we could also do a U substitution and say u equals negative t over 3. Okay, that's negative 1/3 t, so du dt would be negative 1/3, and du is negative 1/3 of dt. I don't have negative 1/3 of dt, I have 1 dt, so 1 dt would be equal to negative 3 times du. Okay, and then I'm going to rewrite my integral. I'm still anti-differentiating e to some power, but now instead of negative t over 3, we can call that u, and then dt is negative 3 du. And we know an antiderivative for negative 3 e to the u with respect to u, that would be negative 3 e to the u plus a constant. And then we can see, okay, that is the same, using u equals negative 1/3 t, the same as what I would have gotten had I tried to do it mentally. All right, now the next one looks like it's going to be a little bit more complicated, but I'm telling you, if you just kind of keep your cool and remember like how we're doing these and preparing for when the inside of a composition of functions is linear, it's really not all that bad. So I've got the square root of a linear function, and the antiderivative of the square root is going to be 2/3 of that thing to the 3/2. Okay, and then the linear function would stay the same, that 5y minus 1, and then I would divide by the slope of the linear function. Remember, this only works when the inside's linear because I can only divide by a constant to make this work. Otherwise, I need a more robust U-substitution, but you would be able to see that that was going to happen because you'd have some sort of like product in your integral. Here, okay, I'd say, I've got this, maybe I need to add a constant, but if I wanted to do this with a U-substitution, I would say let u equal 5y minus 1. Okay, then du dy would be equal to 5, and du is 5 dy. I only have 1 dy, so that would be 1/5 of du. That's where the 1/5 is going to come in. But I'd say this is going to still be an antiderivative of the square root of now u, and then dy is 1/5 of du. Okay, I might rewrite this to make sure I'm execute the power rule correctly. That's u to the 1/2 power. I'm going to add 1 to that power. That's 3/2 divided by that new power. That's where I'd get a 2/3. And 1/5 times 2/3 u to the 3/2 plus c. Okay, and u equals 5y minus 1. This is the same. Okay, so I'm saying that, like with time, you should be able to do this mentally. Students in my class are frequently, very strong doing this process. But I think sometimes it helps to go grind through the U-substitution a few times. All right, now we've got a definite integral. And this one's going to be one of those, I would call it more robust U-substitution. So I'm going to need to let u equal sine x so that du is cosine x dx. Right? And then cosine x times dx is what I've got in my integrand that I kind of want to get rid of, and I could do an antiderivative of 1 over u if I needed to. So u equals sine x, du is going to be cosine x dx, and so I'm all ready to substitute. I'm going to be anti-differentiating 1 over u with respect to u, and then that's going to be the natural log of the absolute value of u. So I'm going to go, okay, say I've got my antiderivative, I'm ready to go, because u equals sine x. So I've got the natural log of the absolute value of u equals sine x, and then I'm going to let x go from pi over 4 to pi over 2. This year I am recommending that we use U-substitution as our tool for anti-differentiation, not necessarily like changing the bounds. I like the thought of us doing it this way. Maybe we see how the substitution works and the anti-differentiation. Also, when we go to do U and V substitution in the spring, that's also my recommendation there, is just use it as an anti-differentiation tool. So I'm trying that this year. I'll do a couple of examples the way I used to do it, where we're going to convert the bounds, because we need to be aware of the fact that if you do convert the bounds, if you do write, bounds on that u integral that I usually write using some colors, they do need to be u coordinates. But if we just do it as an antiderivative, we don't really need to worry about that. Okay, and it gets taken care of in the administration of the fundamental theorem, which is where I'm going to have like, okay, natural log of sine of pi over 2, so it'll be natural log of 1 minus the natural log of the sine of pi over 4. So sine of pi over 4 is root 2 over 2. And then if you wanted to, you could, apply a log property. You could probably apply another one if you wanted to and call out the natural log of, I think, the square root of 2. But, no need for that. The second line there where we have I think I would need that last line there, because in our class we need to evaluate unit circle trig and logs of powers of e, and natural log of 1 is a log of a power of e. Okay, here we've got another full-blown definite integral with u-substitution. We've got x squared over e to the x to the third. Okay, so with an x to the 3 and x to the 2, I'm going to need to let u equal x to the 3. Okay, so I'll figure out the rest later. U equals x cubed du is going to be 3x squared dx. I only have x squared dx, so I need to divide both sides by 3. Say x squared dx is going to be 1/3 of du. Okay, from here, I'm going to start anti-differentiating. I'm going to have the integral of 1 over e to the u times 1/3 of du. Okay, 1 over e to the u. That's not really an antiderivative we have. That type of fraction, we need to rewrite this as a negative power. This one's kind of got 2 u substitutions in it. But I really think that this is the way to go for us, because we need to just kind of know that both the derivative and the antiderivative of e to the negative u with respect to u is going to be negative e to the negative u. Okay, and this time anti-differentiating, so we're dividing by -1, but taking the derivative and multiplying by -1, it's really the same thing. So I'm going to have -1/3 e to the negative u, possibly plus a constant, but since this is a definite integral, I'm not going to worry about that. Okay, and I've got my antiderivative, so I'm going to say, all right, okay, over here I've got -1/3 e to the negative u would be -x cubed, and I'm going to let x go from 0 to 1. And so if I plug in x equals 1, that's -1/3 e to the -1, and then I'm going to subtract, and that would be -1/3 e to the 0, so minus -1/3 is plus 1/3, and there you go, you got yourself an answer. Okay, now number 6. This one is not as obvious how the u-substitution is going to work, especially if you're new to, a u-du change of variables. But if you think about taking the derivative of x squared plus 2x, that's going to be 2x plus 2, and that's off by a constant from x plus 1. And so we're going to be able to proceed like we have been with the other ones. And we just might need to be a little bit more careful with our parentheses. Also, if you see an exponential and we're doing u-substitution, it's going to be the exponent that's going to be the inside of the composition of functions that we need to use as our u. So I'm going to say let u equal x squared plus 2x. Okay, then du dx would be 2x plus 2. And if I multiplied both sides by dx, I would need to put some parentheses around that 2x plus 2. It would be du is all of 2x plus 2 dx. Well, I don't quite have that. I have x plus 1 dx, so that would be half of du. And if I just multiplied 1/2 across the 2x plus 2, I would get 1x plus 1. Okay, and so I've got everything ready to anti-differentiate. I'm going to be anti-differentiating e to the u times 1/2 du. And so that's just going to be 1/2 e to the u. And so I can go over here and write my antiderivative in terms of x. That would be 1/2 e to the x squared plus 2x. And we're going to let x go from 0 to 1. Okay, when we do that, we're going to plug in x equals 1, and we get 1/2 e to the 1 plus 2. So it's like 1/2 e to the 3 minus 1/2 e to the 0. This is going to be 1/2. And there we go. We've got a value. All right. 2x over the square root of 1 minus x squared. Now this one looks a lot like one of those arc trig antiderivatives, but it's not because of the 2x in the numerator. And so that 1 minus x squared, its derivative is very close to 2x. So I think I'm going to be able to use U-substitution on that. So I'm going to say u equals 1 minus x squared. Du would be negative 2x dx. I have 2x dx in my integrand, so I'm going to write that as negative du. Well, I don't know why I would say negative half du. Yeah, that's just definitely regular negative du. Okay, I would be able to write my antiderivative as the antiderivative of 1 over square root u times negative du. And so I'd factor that negative out to the outside. And then I'd say, okay, 1 over the square root of u, I need to rewrite that as a negative power. So it'll be the negative antiderivative of u to the negative 1/2. So I'll add 1 to the power. That'll be u to the positive 1/2. Divide by the new power. Dividing by 1/2 is multiplying by 2. So I'd have negative 2 times u to the 1/2 power. And that's negative 2 times the square root of u. Okay, then I've got my antiderivative. So I'm going to say, okay, negative 2 square root of u, which is 1 minus x squared. And I'm going to let x go from 0 to 1/2. Okay, when I do that, I'm going to plug in 1/2. 1 minus the square of a half is 1 minus a quarter, which is 3/4. So when I plug in 0, there'd be 1 inside the square root. So I'd have negative 2 square root of 3/4 minus negative 2 times the square root of 1. And, you know, that would be a safe place to stop on the quiz. But if we were looking for the right answer on like multiple choice or something, it would probably be written as like 2 minus the square root of 3. All right, number 8. I'm going to let u be the inside of the square root, the inside of the composition of functions. So u equals 4 minus x squared. Du is going to be negative 2x dx. I only have 1x dx, so that would be negative half of du. Make my substitution. The x in dx becomes a negative 1/2 in a du. I'll put the negative 1/2 on the outside of the integral. And the 4 minus x squared inside the square root becomes square root of u. And so I'm thinking about antiderivative of u to the 1/2. That's 2/3 u to the 3/2. And I'm still multiplying by negative half. And those 2's would cancel, so I'd have negative 1/3 u to the 3/2. And so I'll write my antiderivative negative 1/3 of 4 minus x squared to the 3/2, because that's what u is. Okay, and then I will let x go from 0 to 2. And so this will be negative 1/3 of something to the 3/2 minus negative 1/3, so plus 1/3 of something else to the 3/2. And so I plug in 2 for x, and I get 4 minus 2 squared. That's 0. I'm going to put it in there. And then when x equals 0, I'd have 4 to the 3/2. And now, okay, this is probably a safe place to stop, but if you needed to keep going, like say in a multiple choice problem, you need to know that 4 to the 3/2 is the square root of 4 to the 3rd power, so that's 2 cubed. 8 divided by 3, that's going to be 8/3. Right, looks like I didn't space my work very well on this one. I'm a little crammed in on my shot on my video, but this one here is just a regular antiderivative, so I think I can fit it in a relatively small space. So antiderivative of x dx divided by square root of 3x squared plus 5. And of course that's the same as just like having the dx written multiplied off on the right side, but you know, every once in a while we've seen it written in the numerator of fractions. Don't want you to be like, caught off guard if that ever happens. Okay, so I'm going to let u once again be the inside of the square root. That's always a pretty safe bet. So u equals 3x squared plus 5. Then du dx would be 6x, so du is 6x dx. And 1x dx would be 1/6 of du. So if I make my substitution, I'm going to be anti-differentiating. Okay, the numerator becomes 1/6 of du, and the denominator is square root u. Okay, so I could even write it like that. But if I did, and you know I was confused, don't fear, you can just write it as 1/6 of u to the negative 1/2 multiplied by du, because it's still true, right? And then now I'm going to add 1 to the power on u, so that'll be u to the positive half, divide by the new power. It's like multiplying by 2, so I'd have 2/6 or 1/3 u to the positive 1/2 plus c. And I know that u was equal to 3x squared plus 5, so I can make that substitution and say, okay, 1/3 of the square root of 3x squared plus 5, possibly plus a constant. Whoops, I may have just accidentally shown you the answer to this one, but that's no big deal. I'm about to show you how it goes anyway. So again, we've got another square root in a denominator, and that's a pretty common antiderivative to take in AP calculus. Maybe not this common, but with u du, it fits really well. So we're going to let u equal this inside of the square root 1 plus sine theta. So the derivative of u would be cosine theta, so du is cosine theta d theta. That's perfectly what I've got. I'm going to make that substitution. I'm going to have the antiderivative of 1 over the square root of u du, which I've done a couple of times recently, so I might just go ahead and immediately write that as antiderivative of u to the negative 1/2, add 1 to the power, divide by the new power, that's going to be 2u to the 1/2, and I'm ready to go pretty quickly on this one. So this one's going to equal 2 square root of u, which was 1 plus sine theta, and we're going to let theta go from 0 to pi over 2. If I plug in theta equals pi over 2, sine of pi over 2 is 1, so I'd have 2 times the square root of 1. No, 2 times the square root of 2, because it's 1 plus 1. Then minus 2 times the square root of 1 plus the sine of 0, and that's 2 square root of 1. And so, you could stop there, or you could simplify a little farther. It doesn't really matter. Okay, 2 root 2 minus 2. There you go. All right, this next one, we've got kind of the du over u pattern. Okay, and when we have the du over u pattern, we need to use the denominator of the fraction as u. We can also say the derivative of x squared plus 1 is very close to x. Okay, we'll be able to work with that. So u equals x squared plus 1, du is going to equal 2x dx. That means x dx is half of du. And when we do that, I'm going to say, all right, I'm now anti-differentiating 1 over u times 1/2 du. And I can factor out the 1/2 and say that's going to be 1/2 of the natural log of the absolute value of u, and then that's going to be my antiderivative. Go off to the side, say 1/2 natural log of the absolute value of x squared plus 1. Let x go from 2 to 3. And when I plug in 3, I'd have the natural log of the absolute value of 10. That's just the log of 10. And then 1/2 of the log of the absolute value of 5. That's just the log of 5. Okay. Yeah, that's okay. That's not true. It's 5, not 3. Okay, and if you wanted to, you could simplify this using a log property. 1/2 of the log of 10 divided by 5, which would be 2, natural log of 2. But you don't necessarily have to do that, and you don't ever have to simplify with log properties in AP Calculus anymore. All right, now because this one is extremely similar to the last one, I'm going to do this one by actually substituting the bounds and changing the bounds of integration. And if this works better for you, obviously you're free to do this. This is a equally mathematically valid way to approach the problem. I just think that there's more opportunities for linkage errors and confusions and other kinds of errors, especially bounds errors along the way doing it this way. When I originally wrote out the solution to this, I was like kind of crammed in, and I've since spaced it out, but I still think this is a good one for you because it's very similar to the one I just did. So I got that kind of that u prime over u pattern, so I'm going to let u equal x squared plus 2x. Du dx is 2x plus 2. We've done one almost exactly like this in this problem set. So that would be 1/2 du equals x plus 1 dx. And then I'm going to make my substitution, set up for the antiderivative. It's still going to be, okay, the x plus 1 dx becomes a 1/2 on the outside of the integral and a du on the right-hand side of the integral. We're going to be anti-differentiating 1 over u with respect to u. This is all good. But if I want to write bounds on this integral, I need to change everything to u's. Remember what I told you in class. We cannot be mixing x's and u's in our integral. So what I need to do if I want to write bounds on this is convert the x's to u's. And we've been doing this after finding the antiderivative, basically inside of the antiderivative, just plugging in the x values and letting it take care of itself. And I still think that that's going to be the best method for us overall on the population level, but I'm just going to show you how this goes, because this used to be my preferred method of doing these problems in my class. So we would start with, okay, the lower bound is x equals 1. So x equals 1, u equals x squared plus 2x, 1 plus 2, u is going to equal 3. And then when x is 2, u is x squared plus 2x. That's 4 plus 4. That's going to be 8. Oh, no. I said it was 6. Right, so I'm ready to, substitute my bounds. And the lower bound of 1 needs to become a lower bound of u equals 3. And my upper bound of x equals 2 becomes an upper bound of u equals 8. And I can do my antiderivative for 1/2 of 1 over u with respect to u. That would be 1/2 log of the absolute value of u. And then here, where I'm about to put in my bounds of integration, I'm going to let u go from 3 to 8. And so that would be 1/2 of the natural log of the absolute value of 8 minus 1/2 of the log of the absolute value of 3. So 1/2 log of 8 minus 1/2 log of 3. And that would be a safe place to stop. Or I could apply a log property if I wanted to and write it that way. But, once again, you don't have to do that if you don't want. All right, number 13. We're getting close to the end of this set of algebraic problems. X cubed e to the x to the fourth. Okay, right, where a to the x to the fourth. X to the fourth is the inside of the composition of functions, and the derivative of x to the fourth is proportional to x to the third, so I'm going to be able to use u du. All right, so I'm going to let u equal x to the 4. Du dx is going to be 4x cubed, so du is 4x cubed dx. I have 1x cubed dx, so that would be 1/4 of du equaling x cubed dx. And I'm going to say, all right, my antiderivative is the antiderivative of e to the u times 1/4 du. And antiderivative for e to the u with respect to u is e to the u, and still multiplying by 1/4. So I'll go off to the side and say, all right, this is going to be equal to 1/4 of e to the x to the fourth as x goes from 0 to 1. Okay, and when x is 1, this is 1/4 e to the 1, and when x is 0, this is just 1/4 of e to the 0, which is just 1/4. So 1/4 e minus 1/4. Now, number 14, this one looks bad at first glance, but if you see what's going on, it's really going to work out nicely. So the cosine squared x and the tangent x and the exponential, it's like, okay, well, we know that the exponential, the exponent probably needs to be the inside of the composition of functions we're going to use as our u. I know an antiderivative for e to the u, but that cosine squared x, what we need to realize is that a cosine squared x in a denominator is the same as multiplication by secant squared x. And I think if I rewrite this integral as the integral from 0 to pi over 4 of e to the tangent x times secant squared x dx, you'll see the u-substitution a lot clearer. And I'm going to let u equal tangent x. The derivative of tangent x is secant squared x, so this is going to be a perfect match. Du is secant squared x dx. Okay, so I'm ready to anti-differentiate. I can say, all right, I'm going to anti-differentiate e to the u with respect to u. This is great, e to the u. So the antiderivative I'm looking for is, okay, e to the u. That's e to the tangent x, as x goes from 0 to pi over 4. And so I'm going to have e to the something minus e to the something else. And so I need to think about tangent of pi over 4 and tangent of 0. I'm going to plug in tangent of pi over 4. At pi over 4, I've got that 45, 45, 90 triangle where the height and the width are equal. So tangent opposite over adjacent, that's going to be 1. Or you could say sine of x over cosine x, and at pi over 4 they're the same, so their ratio would be 1. And tangent of 0, sine of 0 over cosine of 0, or however you want to think about it, tangent of 0 is going to be 0. And so e to the 1 minus e to the 0, that's just e minus 1. All right, now this last one's a little bit tricky, and this one I also kind of had the work crammed in, so I'm going to be converting the bounds on this one. But before I even get started in on all of the different things where you could go wrong in this, I just want to point out that this integral is like kind of backwards, pi over 2 to 0. Pi over 2 is greater than 0, so if I'm going backwards from pi over 2 to 0 on this function that's sine of x multiplied by cosine squared x, both sine and cosine are positive on the interval 0 to pi over 2. and the cosine squared. So this function is definitely positive the whole time, positive or zero. So I'm integrating a positive function backwards. I need to get a negative value for this integral. So like if I don't get a negative number, that would be cause for concern. I need to go back and check. And it would be really easy to get messed up, especially if you do this bounds changing thing that I'm about to show you. But I think maybe if I show you this and you see where I could easily see where I could get that backwards, then maybe you'll see why I'm recommending we just use the UDU as an anti-differentiation technique. Okay, now first, we've done derivative of sine is cosine and derivative of cosine is negative sine. We're never going to want to have an expression like du squared or cosine of du or anything like that. Okay, so what we're going to need to do is maybe rewrite the cosine squared x as a cosine x with parentheses around it squared. And if we do that, and then also put the sine x next to the dx, I think it makes it a little clearer what we're going to be doing with our U-substitution. Okay, with a thing squared, I need to let u equal cosine x. It's the inside of the parentheses. So I'm going to let u equal cosine x so that du is negative sine x dx. But I have positive sine x dx, so that'll be negative du. I'm going to set up my integral, and that's going to be still an antiderivative of something squared. Okay, and the cosine, that's u. And then the sine x dx became a negative and a du. Right? And if I'm going to put bounds on this integral, I've got to convert everything to u's. So I can't have like pi over 2 to 0 in this because that would be untrue. Okay, those two things would not be equal. That would be like a communication error, linkage error. And we don't want to do those. So I'm going to start in thinking about converting my bounds. When x equals pi over 2, u equals the cosine of pi over 2. So pi over 2, cosine of pi over 2 is 0. So I'm going to plug in that lower bound. That lower bound of pi over 2 is now a lower bound of u equals 0. And when x equals 0, cosine of 0 is equal to 1. So x equals 0 gives me u equals 1, and I'll plug that in as my upper bound. And then this, the integral from 0 to 1 of thing squared, or u squared du, that's going to be really easy. And that's the whole idea of U-substitution, is take a difficult integral and make it much, much easier. All right, so I'm going to say that's just the negative of 1/3 u to the third and let u go from 0 to 1. And then that'll give me the negative of 1/3 minus 0, and that's that negative number I was expecting all along. And that's kind of surprising to me that sine and cosine, they take on these really weird bad decimal values all the way between 0 and pi over 2. But the amount of area under this graph was actually 1/3, and we made it negative because we were integrating backwards. Okay, and that 1/3, that's a really nice round number. So it's kind of unexpected. All right, now we're going to move on to some different problems that are going to hopefully at least have some degree of U-substitution on. This one's one where I'm hoping we can maybe do the U-substitution mentally. We've got the integral from -1 to 1 of f of x dx. And so I'm going to need to split that up, right, because the function splits at x equals 0. So from -1 to 0, I'm going to need to be thinking about that portion of the function where x is less than 0, and from 0 to 1, I'm going to need to think about the portion of the graph where x is greater than or equal to 0. So I'm thinking, all right, x less than 0, that's the x plus 1, where I'm going to integrate from -1 to 0, and the x greater than or equal to 0, that's when I'm integrating cosine of pi x from 0 to 1. Okay, actually administering these integrals, okay, the blue one should be pretty easy. Anti-differentiate x plus 1, that would be 1/2 x squared plus x, as x goes from -1 to 0. Plug in 0, plug in 1, do your subtraction, 0 minus -1/2, that's going to be 1/2. Okay, then I will look at the red integral, and an antiderivative for cosine of pi x would be sine of pi x, but I need to divide by pi to prepare for the chain rule, right? I can just divide by a constant mentally. That's no big deal. And then let x go from 0 to 1. And then I'm thinking about sine of pi and sine of 0. It's like, wait a second, both those are 0. So I'm going to have 1 over pi times 0 minus 1 over pi times 0, and that's no area. Okay, so that's kind of weird, but okay, 1/2 plus 0, that's going to be 1/2. And so I was thinking about this, and I was like, oh, it's kind of weird that I got 0 on both of these. Like, what's going on with this graph? And it's like, y equals cosine of pi x. that's a function I can sketch the graph of. So I went off to the side and I sketched the graph of this, and so you can kind of try to figure out what's going on here. And I saw, okay, yeah, because of that multiplier of pi, as x goes from 0 to 1, that's cosine going from the top of its graph to the bottom of its graph, and it's got that symmetry to it. So I'm seeing why that red integral gave me 0. And then I just went ahead and added the x plus 1. It's like, oh yeah, that was a triangle that had base and height equal to 1, so it made a lot of sense that its area was a half. So if you draw a picture of this, it made a lot of sense what was going on there. All right, now we're going to compute an average value. We learned about average value last time. Can't have you forgetting about that. So remember, the average value of a function on the interval 0 to 2 is going to be 1 over 2 minus 0 times the integral from 0 to 2 of f of x dx. And this is going to require U-substitution. So inside of the square root, safe bet for u equals x to the 3 plus 1. Yes, this is looking right. Du is 3x squared dx. So x squared dx is going to be 1/3 of du. And I'm going to make my substitution, do my antiderivative. So that'll be the antiderivative of the square root of u times 1/3 du. Okay, so it'll be 1/3 of 2/3 u to the 3/2. And then I could probably combine those fractions and make that 2/9 u to the 3/2. And so I've got that over here. And remember, I'm still multiplying by a half because I'm still taking an average value. Okay, just don't want to lose track of that. Okay, so 1/2 of 2/9 u to the 3/2. U is x to the 3 plus 1. Let x go from 0 to 2. And so it's going to be a 1/9 on the outside. 2 to the 3rd plus 1. 0 to the 3rd plus 1. So I'm taking 9 to the 3/2 minus 1 to the 3/2, and for your response, safe stop here. But I could definitely see this being a multiple choice question. We like to use those fraction exponents on a multiple choice question. And we need to know that 9 to the 3/2 power is the square root of 9 cubed, so it'd be 27. Any power of 1 is 1. That's where I would get 26 divided by 9. All right, now number 18. This one, I think this one's a little tricky. I know I've taken this one from, I think it's a released multiple choice question. But this is related to a U-substitution as well. And this is one where we're going to have to be thinking about the balance for sure. So I definitely like this, in comparison to the ones that I've been doing, just U du as an antiderivative trick. We need to be aware that if we change bounds, if we have bounds on a converted integral, we need to have converted bounds. Is what I'm saying. So I'm going to work on the integral on the right, f of 5 minus x, right? Because the integral of f of x dx equaling 6, there's not really much for me to do with that. I'll hopefully use that later. So this integral on the right, I'm going to hopefully use some u substitution on it. And I don't really know what else to do besides u equals 5 minus x, the inside of the parentheses. Okay, u equals 5 minus x, du dx would equal -1, so du is negative dx. I just have dx, so maybe I'll say dx is negative du and just start to try to put the pieces together on this integral and see what are they trying to get at here. So I'm definitely going to still be integrating. Yes, I was saying I need to convert the bounds as well. So 5 minus x, if x is 1, u is 4. And if x is 4, u is equal to 1. Yeah, that upper bound of that integral is 4, not 5. Okay, and that makes more sense. And now I'm starting to see where they're getting at. Okay, so it's kind of got changed bounds, but okay, what's going on here? So I'm still integrating, and there's still an f. I haven't really changed anything about that. I don't really know what I would do with it. But that 5 minus x has become a u. And then the dx is a negative and a du. Okay, if I change the bounds, which it looks like I'm going to have to do, the lower bound of x equals 1 becomes a u equals 4, and the upper bound of x equals 4 becomes a u equals 1. It's like, okay, well, the negative of the integral from 4 to 1, well, that's kind of like backwards bounds, so I could apply the negative to the bounds and reverse the bounds and say, okay, this is the integral from 1 to 4 of f of u du, but that's going to also equal 6. Because the integral from 1 to 4 of f of u du, that's the same as the integral from 1 to 4 of f of t dt, is the same as the integral from 1 to 4 of f of x dx. If you actually think about it, if you had a formula for f, whether it was written with u's, x's, t's, y's, any variable, the act of taking the antiderivative and plugging in the 1 and 4 it'd just be the different letters. There wouldn't be really any change in the process. So that's why this one's also going to be 6. All right, this one, I'm not sure how this one got here. I don't really understand what it has to do with U-substitution. I don't really think it has anything to do with U-substitution, but it's kind of a nice little problem. So f of x is g of x plus 7, and we've got the value of the integral from 3 to 5 of g of x dx, and they're going to ask us about the integral from 3 to 5 of f of x plus g of x dx. So I might say, all right, well, I'll just plug in on f of x and call that g of x plus 7. So rewrite my integral as the integral from 3 to 5 of g of x plus 7 plus another g of x. And I've kind of got all the information I need to solve this, right? The integral of g is 10, so I'm going to start out, okay, from the first g, that's a 10, plus 7 times 2, because it's spread out over 3 times 5, and I'll draw you a picture of that in a second. Then plus another 10, and that's going to end up being like, I don't know, 10, 20, 34. But if you were confused about the 7 times 2, just think about, like, remember this is like f of x equal, or not f of x, y equals 7 on the interval 3 to 5. So it would be a rectangle with height 7 and width 2, and that's why I've got the 7 times 2 right there. And so if I add those together, I'm going to get 34. Okay, now we're closing in on the end of this problem set. We're on the last page, so we've got to be getting close. We've got an acceleration of the particle given by a of t is e to the negative 2t. If at t equals 0, the velocity is 5 halves and the position is 17/4, then the position at any time t greater than 0 is, okay, so we're going to just solve for x of t using anti-differentiation and finding the c. Okay, and then, the U-substitution will be the fact that we've got that e to the negative 2t. But I don't think we need a U-substitution for that. I think we can just think about the chain rule, mentally check our antiderivative by taking a derivative. So I'm going to start out by saying, okay, they told me that a is e to the negative 2t. Velocity is going to be an antiderivative for that. So antiderivative for e to the negative 2t with respect to t, well, that should be related to e to the negative 2t. And I could divide by a number to prepare for the chain rule, and I'm going to divide by negative 2. And then I'm going to think about taking the derivative of this, right? The derivative of this would be negative 1/2 e to the negative 2t times negative 2 for the chain rule. So that would give me that 1 e to the negative 2t I have in my integrand. And I might also add a plus c. Okay, then I'll use that initial velocity they gave me, 5 halves. So I'll say velocity is 5 halves when t is 0. So 5 halves is going to equal negative 1/2 e to the 0 plus c. And e to the 0 is 1. So if I added that 1/2 to both sides, I would get 6 halves. And so that's telling me c is equal to 3. So I can write my velocity formula. Velocity is going to equal negative 1/2 e to the negative 2t plus 3. And then if I want the position is going to be the antiderivative of velocity. So I'm going to have an antiderivative of negative half e to the negative 2t plus 3 with respect to t. Then I'm going to antidifferentiate, and an antiderivative for e to the negative 2t should be related to e to the negative 2t, but I'm going to once again divide by negative 2 for the same reason I did up above. And so that'll be positive 1/4 e to the negative 2t. Antiderivative for 3 is going to be 3t. And then I'll have some new constant that I'll need to figure out using that 17/4. So I'll plug in x equals 17/4, and that'll be equal to what I get when I plug in 0 for t. So 1/4 e to the 0 plus 3 zeros and c. And so, okay, 17/4 minus 1/4, so fourth would be 16/4, and this c is going to equal 4. And now I'm ready to write my position formula. That's going to be x of t is 1/4 e to the negative 2t plus 3t plus 4. There we go. Now this is a slightly different type of U-substitution. This is the type that we really don't see very often in AP Calculus, and the type that I don't think we need to be able to think of ourselves, just maybe recognize it a multiple choice problem and kind of just follow the trail that they give us. And they tell us the substitution you need to make, u equals x divided by 2, but even then there's going to be a little bit of trickery here. So I'm going to start with u equals x over 2, so du would be half of dx. I don't see a half anywhere besides that x over 2 that I know that's going to become u. Okay, but even still, like this is not the typical u substitution we've been making so far. This is not the f prime of g of x times g prime of x pattern, that u du pattern that we're used to seeing. All the same, we're going to be able to solve this one. It's not going to be too bad. Okay, but if I just have 1 dx, I'm going to probably call that 2 du. Okay, and then I'm also going to convert the bounds, because this is one of those multiple choice problems where we're saying, like, how do you convert the integral from one integral to another? This is where we have to swap the bounds. So if u is half of x, it should be pretty easy to convert 2 and 4 to 1 and 2. So x equals 2 gives me u equals 1, and x equals 4 gives me u equals 2. And I'm going to start converting my integral. Okay, but this is the conversion, is the tricky part, and that's what they're getting at here. So I need to think I'm still integrating a fraction. I can see that in all the answer choices. And the numerator, I'm pretty confident that's going to be 1 minus u squared. Like, what else would it be? You can see that in the answer choices too. But the denominator, this x, it's like, okay, what am I going to do there? Now, you can look to the answer choices for some guidance, right? I've got a and b having u in the denominator. That doesn't seem quite right. If I solve for x out of the initial substitution that they gave me, I'd have x equals 2u. So I'm just going to make that substitution down there. I'm going to have 2u. And then I have dx is 2 du. So I might write it there and throw in my converted bounds. And I think that the first place, then we're going to go start eliminating answer choices. The first place I'm going to want to eliminate answer choices is on the bounds, right? I need to have that 1 and 2. 2 and 4 are x values, so it would be erroneous to, answer B or E. So I'm going to get rid of those immediately. And then I'm going to look at that 2 in the numerator on the outside and the 2 in the denominator from that substitution. Those are going to need to cancel off. Right? C is wrong because it doesn't have the 2 on the outside, and D is wrong because we've applied the 2 to the denominator when it's not division by 2. So I'm going to eliminate both of those, and that leaves me with A, right? The 2's are canceling. I've got this kind of weird expression there, and it's like, okay, there we go. So the one that I thought was wrong because I had that u in the denominator, it's like x is not equal to u is half x. That ended up being right. Okay, so that's kind of like what I might call like a sideways u substitution. That's not a very common one. I think I'll have one for you like in the practice problems for the quiz, but not the type that we're going to really see beyond that. All right, and here we are. We're at our last problem, and this is one that we could do with a u substitution if we wanted, converting the bounds and everything, or not, however you want to do this. But I think this is one that's going to be easiest, fastest, and safest to try to do just anti-differentiating mentally. Now, the first thing, and this is something we haven't run into a whole lot yet, but we will see more and more as time goes on, is this, okay, f is a continuous function, and capital F prime equals f for all real numbers x. So f, our f, lowercase f, is the derivative of uppercase f. That means that uppercase f is the antiderivative for our lowercase f. And I'm just going to write that off to the side just so I have that clearly and I can remember that when I go to anti-differentiate. So if I'm trying to anti-differentiate f of 2x, our f, lowercase f of 2x, it should be capital F of 2x divided by 2 to prepare for the chain rule, because the derivative of capital F of 2x would be capital F prime of 2x times 2 for the chain rule. We want to have 1 capital F prime of 2x, because that's lowercase f of 2x. All right, so I'm going to anti-differentiate and get 1/2 uppercase f of 2x. And we're going to let x go from 1 to 3. So we're going to have a difference in two values that's like 1/2 f of something. So I'm going to kind of set that up and think about plugging in 3 for x, right? So I'm going to have 1/2 f of 6 minus 1/2 f of 2. Plug in that 3 and get 6, plug in the 1 and get 2 on the inside of f, and then I can see, okay, this is going to be answer choice E. Right, and I feel like maybe there was something else I had to say about this one, but, this one is the type of problem, I really like this one for a variety of reasons. It's the one I've got a few different versions of this one, so you might see this one again. Who knows? Depends on the year, what I'm going to use on my unit test, but it's always a safe bet I'm going to have something, not too far off from this. All right, so that's going to be all for this video. Thanks for watching.